Before we dive into one of the most decisive technological shifts of the Pacific War, hit that like button, subscribe, and drop a comment telling us where you're watching from. Today's story isn't about a new aircraft or a secret weapon. It's about a single type of ammunition that transformed American fighter pilots from underdogs into hunters, and turned the fearsome Japanese Zero from an invincible predator into vulnerable prey. December 1942. Over the Solomon Islands, a Japanese Zero pilot watches an American Wildcat far below. Too far for effective fire, or so he thinks. He begins his attack dive, confident in his superior position. Then, at 800 yards, the American opens fire. The Zero's wing erupts in white-hot flame, magnesium burning at temperatures that can't be extinguished. The pilot barely has time to register shock before his fuel tank ignites. 800 yards. The Americans weren't supposed to be able to kill at that range. But they were doing it, again and again. This is the story of the M8 Armor-Piercing Incendiary round, a technological innovation that fundamentally altered the balance of power in the Pacific War. It's a story that matters because it demonstrates how wars are won not just by brave pilots or superior aircraft, but by the bullets those aircraft fire and the tactics used to employ them. By late 1942, American fighter pilots faced a crisis. Japanese aircraft, particularly the legendary Zero, had dominated Pacific skies since Pearl Harbor. American fighters were often slower, less maneuverable, and their pilots less experienced. Standard ball and armor-piercing ammunition required multiple hits to bring down enemy aircraft. Pilots had to get dangerously close, within 400 yards, to have any real chance of a kill. At those ranges, Japanese pilots could outmaneuver American fighters and return devastating fire. The stakes were measured in blood and aluminum. In 1942 alone, American naval aviation lost over 1,100 aircraft in combat. Every bomber that fell meant 10 men dead. Every fighter pilot shot down represented hundreds of hours of irreplaceable training. The United States was producing planes faster than any nation on Earth, but it couldn't train experienced pilots quickly enough to replace losses. Something had to change. That change came not from the drawing boards of aircraft designers, but from the ammunition plants and proving grounds where engineers were perfecting a round that would combine penetration with incendiary effects, a bullet that wouldn't just punch through an enemy aircraft, but would set it ablaze from the inside. The M8 API round would prove to be one of the most decisive technological advantages of the war. To understand the story, we need to go back to the beginning, to the weapon platform itself, the legendary Browning M2.50 caliber machine gun. Developed by John Moses Browning in the aftermath of World War I, this weapon was born from a specific request by General John J. Pershing, who had witnessed German armored aircraft shrugging off .30 caliber rounds. Pershing demanded a machine gun with a caliber of at least .50 inches and a muzzle velocity of at least 2,700 feet per second. Browning delivered, creating what would become the most successful heavy machine gun in history. By the time America entered World War II, the aircraft-mounted version, designated and /M2, armed virtually every American fighter and bomber. The P-51 Mustang carried 6 of them. The P-47 Thunderbolt mounted 8. The P-38 Lightning paired 4.50 caliber guns with a 20 mm cannon. Even bombers like the B-17 Flying Fortress bristled with up to 13.50 caliber positions. These weapons could fire between 750 and 850 rounds per minute, and their .50 BMG cartridge delivered devastating kinetic energy at the muzzle, over 18,000 foot-pounds. But kinetic energy at the muzzle doesn't win air battles. What matters is what happens when bullets strike enemy aircraft at combat ranges. And in early 1942, American pilots were discovering that their standard ammunition, M2 ball rounds and M2 armor-piercing rounds, weren't doing enough damage quickly enough. The problem was physics. A .50 caliber ball round is essentially a large lead core wrapped in a copper jacket. When it hits an aircraft, it punches a neat hole and keeps going. Against unarmored targets, it causes damage primarily through the wound channel it creates. But aircraft aren't made of flesh, they're aluminum frameworks wrapped in thin metal skin. A ball round could punch through a wing, miss every critical structure, and exit the other side having accomplished nothing more than creating 2 small holes. The M2 armor-piercing round was better. It featured a hardened steel core designed to penetrate armor plate, and it could certainly punch through engine blocks and structural components. But it still didn't create the kind of catastrophic damage that stopped enemy aircraft reliably. Pilots reported needing dozens of hits to bring down a single enemy fighter. In a dogfight where you might only have 3 to 5 seconds of firing time before your target maneuvered away, that wasn't good enough. Making matters worse, American pilots were facing an enemy aircraft that seemed almost supernaturally capable. The Mitsubishi A6M0 had shocked Allied air forces when it first appeared in combat over China in 1940, and by December 1941, it had established air superiority from the Philippines to New Guinea. With a maximum speed of 331 miles per hour and a phenomenal turning radius, the Zero could outclimb, outturn, and outrange virtually any Allied fighter in service. Its two 20mm cannons and two 7.7mm machine guns provided formidable firepower. Japanese pilots weren't just flying superior aircraft, they were among the best-trained aviators in the world. Many had thousands of hours of flight time and years of combat experience from the war in China. They flew with samurai-inspired aggression, pressing attacks with fearless determination. American naval aviators called the early months of 1942 the time of the Zero, because Japanese fighters seemed almost invincible. But the Zero had a fatal weakness, one that American intelligence would eventually exploit with devastating effectiveness. In their pursuit of range and maneuverability, Japanese designers had made critical compromises. No armor protection for the pilot, and most critically, no self-sealing fuel tanks. This meant that while the Zero could outmaneuver American fighters, a single well-placed burst into its fuel system would turn the graceful aircraft into a flying torch. By mid-1942, American fighter pilots in the Pacific faced a brutal mathematics of survival. Combat reports told a grim story. It took an average of 20 to 30 hits from .50 caliber machine guns to bring down a Japanese fighter. In contrast, Japanese 20mm cannons could destroy an American fighter with just 2 or 3 hits. The Zero could engage American fighters from 600 yards with its cannons, while American pilots had to close to 400 yards or less for their machine guns to be truly effective. Lieutenant Commander Edward Butch O'Hare, who would later receive the Medal of Honor for single-handedly defending the carrier USS Lexington against 9 Japanese bombers, described the problem in his after-action reports. On February 20, 1942, he had fired approximately 400 rounds to bring down 5 Betty bombers, an average of 80 rounds per kill. Bombers were large, relatively slow targets compared to fighters. Against the nimble Zero, pilots were expending 2 to 3 times that amount of ammunition for uncertain results. The tactical implications were severe. American fighters like the F-4F Wildcat carried only 1,440 rounds total, 240 rounds per gun across 6 guns. The F-4U Corsair carried 2,400 rounds. At 80 to 100 rounds per kill, pilots had ammunition for perhaps 15 to 20 seconds of sustained fire, and combat experience showed they might only achieve 2 or 3 kills before running dry. Compare this to Japanese pilots, whose 20mm cannons, though they carried only 60 rounds per gun, could score kills with devastating efficiency. Range was another critical problem. Effective range, the distance at which a pilot could reasonably expect to hit and damage an enemy aircraft, was determined by several factors: bullet trajectory, time of flight, and the destructive power of the round upon impact. Standard ball ammunition maintained lethal velocity to about 1,000 yards, but hitting a maneuvering target beyond 400 yards was extremely difficult, and even successful hits often failed to cause enough damage to bring down the target. This range limitation forced American pilots into close-quarters combat, exactly where the Zero excelled. Japanese pilots were trained in dogfighting tactics that exploited their aircraft's superior turning ability. They could force American pilots into turning engagements where the Zero's advantages were overwhelming. American pilots who tried to disengage found that the Zero could often follow them, and while the Japanese fighter couldn't catch up in a straight-line dive or high-speed chase, it could harry them all the way back to base. Marine Captain Marion Carl, who would become one of the war's top aces with 18.5 confirmed kills, described the desperate situation in his memoir. During the defense of Guadalcanal in August 1942, his squadron faced overwhelming numbers of Zeros. "We had to get close, really close, to make kills," he wrote. "That meant exposing ourselves to their fire. We lost 3 pilots for every Zero we knocked down. It wasn't sustainable." The casualty figures bore out Carl's assessment. During the 6-month campaign for Guadalcanal from August 1942 to February 1943, The United States lost 420 aircraft in combat against 352 Japanese aircraft destroyed. The Americans were winning through attrition, overwhelming Japanese forces with sheer numbers, but the exchange rate was barely favorable and came at a terrible cost in trained pilots. Ground crews and armorers saw the problem from a different angle. When fighters returned from combat, armament officers would inspect the guns and examine remaining ammunition. They discovered that pilots were often returning with half their ammunition unexpended, not because they were timid, but because they simply couldn't get close enough to enemy aircraft to use it effectively. Conversely, aircraft that did engage at close range often returned with battle damage severe enough to write off the aircraft. Technical analysis revealed another dimension of the problem. The M1 tracer rounds that pilots relied on to adjust their aim were actually contributing to the difficulty. These rounds burned brightly, making them easy to see, but they also had different ballistic characteristics than ball or armor-piercing rounds. Their trajectory diverged from the main rounds at longer ranges, meaning pilots who used tracers to walk their fire onto target were actually aiming incorrectly. Additionally, the incendiary composition in M1 tracers began burning in the gun barrel, gradually eroding the rifling and reducing accuracy over time. Intelligence officers studying Japanese aircraft wrecks made a crucial discovery in mid-1942 when they examined the intact Zero captured on Akutan Island in Alaska. The aircraft's fuel tanks had no self-sealing capability whatsoever. A ruptured fuel tank wouldn't just leak, it would spray atomized fuel directly into the slipstream, where a single spark could ignite it. Even more remarkably, the Zero's fuel tanks were positioned in the wings, close to the aircraft's center, where any fire would quickly spread to the main structure. This discovery changed everything. American pilots didn't need to riddle enemy aircraft with dozens of hits. They needed ammunition that could penetrate to the fuel system and ignite it. They needed incendiary ammunition, but not the barrel-burning M1 rounds they currently had. They needed something new. The answer came from Frankfurt Arsenal in Philadelphia, where ammunition engineers had been working on a revolutionary new design, the M8 Armor-Piercing Incendiary round. Development had actually begun before America entered the war, inspired by British experience in the Battle of Britain, where RAF fighters had found devastating success with DeWilde incendiary ammunition against German bombers. American engineers studied the British rounds and set out to create something even better, a round that combined armor penetration with incendiary effects in a single package. The M8 API was an engineering marvel. Unlike standard incendiary rounds that began burning in the gun barrel, the M8 used a different principle. The bullet consisted of three main components: a hardened steel penetrator core at the tip, an incendiary composition in the middle, and a lead base. The steel penetrator was designed to pierce light armor plate and the aluminum skin of aircraft. Behind it, the incendiary composition contained magnesium, barium nitrate, and other compounds that would ignite upon impact, but only after the round had penetrated its target. This was the critical innovation. The M8 didn't burn going down the barrel like the M1 tracer. It remained inert until the moment of impact, when the sudden deceleration and the heat generated by penetrating the target triggered the incendiary composition. Once ignited, it burned at temperatures exceeding 4,000 degrees Fahrenheit, hot enough to melt through aluminum structural members, ignite fuel vapors, and set hydraulic fluid ablaze. The round's external appearance was distinctive, a silver aluminum tip that protected the steel penetrator and gave the round its recognizable signature. This silver tip became infamous among Japanese pilots, who would come to associate it with sudden, catastrophic aircraft fires. But developing the round was only half the battle. Production was another challenge entirely. Manufacturing M8 API rounds required precision assembly. Each round had to be carefully loaded with exactly the right amount of incendiary composition. Too little and it wouldn't ignite reliably, too much and it might become unstable. The steel penetrators had to be heat-treated to exact specifications. Quality control was critical because a single defective round in an ammunition belt could cause a gun jam at the worst possible moment. By early 1943, production had ramped up sufficiently to begin widespread deployment to combat units. The timing was fortuitous. American aircraft production was reaching its peak. New fighter models like the F-6F Hellcat and F-4U Corsair were entering service in large numbers, and American pilot training programs were finally producing enough qualified aviators to replace losses and expand the force. But having the ammunition was only the beginning. Someone had to figure out how to use it effectively. Enter the squadron armorers, the unsung heroes of this story. These were the men who loaded thousands of rounds of ammunition into aircraft before every mission, who maintained the guns, who cleared jams and replaced worn barrels. They began experimenting with different loading patterns for ammunition belts. Standard practice had been to load mixed belts, one ball, one AP, one tracer, repeating. The theory was that variety gave pilots options and the tracers helped them aim. The armorers started questioning this assumption. Why load tracers at all if the M8 API was more accurate and more effective? Why include ball rounds when API did everything ball did plus ignite targets? Through trial, error, and careful attention to combat results, they developed new loading patterns. By mid-1943, the most common loading pattern for fighter aircraft became predominantly M8 API with occasional tracers, typically one tracer every 10 rounds, used only as a low ammunition warning rather than an aiming aid. Some squadrons went even further, loading pure M8 API belts with no tracers at all. Pilots learned to aim using their gun sight reticles rather than watching tracers, and they found their accuracy actually improved. The results were immediate and dramatic. Pilots who had previously needed 80 to 100 rounds per kill were now bringing down enemy aircraft with 20 to 30 rounds. Effective engagement range increased from 400 yards to 600 to 800 yards. Japanese fighters that had seemed impossibly tough were now exploding after single 2-second bursts. Lieutenant Commander John Thatch, who had developed the famous Thatch Weave defensive tactic, became one of the first senior officers to recognize the significance of the M8 API. In a memo to the Bureau of Ordnance in June 1943, he wrote, "The new incendiary ammunition has changed the character of air combat in the Pacific. Pilots report that Japanese aircraft appear to be far more vulnerable than previously assessed. What we initially attributed to better pilot training is in fact largely the result of superior ammunition. Enemy aircraft that previously required sustained fire now frequently explode after brief engagement." Training protocols were updated to reflect the new capabilities. Gunnery instructors taught pilots to engage from longer ranges, taking advantage of the M8 API's effectiveness. The preferred tactic became the boom and zoom approach, diving from altitude, firing a burst from 600 to 800 yards, then climbing away before the enemy could respond. This played to the strengths of American fighters, which were generally faster and more powerful than Japanese aircraft, but couldn't match them in turning fights. The P-38 Lightning particularly benefited from the new ammunition. Its nose-mounted guns, 4.50 caliber machine guns and 120 mm cannon, concentrated fire in a tight pattern. With M8 API loaded, P-38 pilots found they could engage Japanese fighters from 1,000 yards with reasonable hit probability and devastating results. Major Richard Bong, who would become America's top ace with 40 confirmed kills, flew the P-38 exclusively and credited the M8 API with many of his victories. Production statistics tell the story of the M8 API's adoption. In 1942, American factories produced approximately 200 million rounds of .50 caliber ammunition, with less than 5% being API variants. By 1943, total production had increased to 450 million rounds, with M8 API comprising nearly 40% of the total. By 1944, the M8 API was the standard round for fighter aircraft, with other types being used only in specialized roles. The adoption wasn't without challenges. Some pilots initially complained that pure API belts meant they couldn't see their bullets in flight, making it harder to adjust aim. Squadron commanders had to retrain these pilots to trust their gun sights. There were also logistics challenges, ensuring that every forward base, every carrier, every remote airstrip had adequate supplies of the correct ammunition. The Navy's Bureau of Ordnance and the Army Air Force's Air Service Command performed miracles of logistics, shipping millions of rounds across thousands of miles of ocean. Perhaps the most telling endorsement came from the pilots themselves. By late 1943, when given a choice between different ammunition loadings, combat pilots overwhelmingly chose maximum M8 API loads. They had learned through experience that these silver-tipped rounds meant the difference between survival and death, between shooting down the enemy and watching him escape to fight another day. The impact of the M8 API ammunition on Pacific air combat was profound and measurable. By comparing combat statistics from before and after its widespread adoption, we can see its effects with startling clarity. In 1942, American pilots needed an average of 83 rounds of .50 caliber ammunition to achieve one aerial victory. By late 1943, after the M8 API became standard, that figure had dropped to 31 rounds per kill, a reduction of more than 60%. This wasn't just an incremental improvement, it represented a fundamental shift in the lethality of American air power. The Battle of the Philippine Sea in June 1944, known to American pilots as the Great Marianas Turkey Shoot, demonstrated the new reality. Over 2 days, American carrier-based fighters shot down approximately 550 Japanese aircraft while losing only 29 of their own. The kill ratio was 19-1. While superior American aircraft like the F-6F Hellcat and better-trained pilots played crucial roles, post-battle analysis showed that ammunition effectiveness was a critical factor. Japanese aircraft were dying after single passes, often exploding in mid-air before they could maneuver or return fire. Commander David McCampbell, who shot down 9 Japanese aircraft in a single mission during this battle and would finish the war as the Navy's top ace with 34 kills, later testified to Congress about the ammunition's effectiveness. "We were killing them at ranges I wouldn't have attempted a year earlier. 600, 700 yards. We'd open fire and watch them burn. The Zeros, the Judas, the Vals, they all went down the same way. You'd see that silver flash when your rounds hit, then fire, then they'd start coming apart." The psychological impact on Japanese pilots was severe. Surviving Japanese aviators reported deep fear of American fighters in interviews conducted after the war. They described the terror of seeing their wingmen explode without warning, of watching aircraft that seemed undamaged suddenly burst into flames. Some Japanese pilots reported refusing to engage American fighters at ranges beyond 400 yards because they had learned that American pilots could kill from distances the Japanese couldn't effectively return fire. Petty Officer First Class Saburo Sakai, one of Japan's top surviving aces with 64 confirmed kills, wrote in his memoir, Samurai, about the change he observed in mid-1943. American fighters had become much more deadly. Before, we could absorb damage and continue fighting. After the summer of 1943, any hit seemed to cause fire. Our beautiful Zeros burned like paper airplanes. I watched too many comrades die in flames. The ammunition's effectiveness wasn't limited to fighters. B-17 and B-24 bomber gunners, who faced kamikaze attacks later in the war, found that the M8 API gave them a fighting chance against suicide aircraft. Kamikaze tactics relied on Japanese pilots accepting certain death to crash into American ships. But even suicidal pilots couldn't complete their mission if their aircraft disintegrated before reaching the target. B-24 waist gunners reported that kamikaze aircraft approaching their formations would often explode 200 to 300 yards away when hit with API fire, close enough to be terrifying but far enough to be harmless. The strategic implications were enormous. With ammunition now being used more efficiently, aircraft could carry fewer rounds without sacrificing combat effectiveness. This meant either lighter aircraft with better performance or more fuel for extended range. The P-51 Mustang, which began escorting B-29 bombers all the way to Japan in 1945, benefited particularly from this trade-off. Its 6.50 caliber guns carried a total of 1,880 rounds, less than many earlier fighters, but this proved entirely adequate with M8 API loaded. Statistical analysis of combat operations reveals the ammunition's impact on loss rates. In 1942, the U.S. Navy lost 1,055 aircraft in air-to-air combat in the Pacific. In 1943, despite flying far more sorties, losses dropped to 728 aircraft. By 1944, even as the tempo of operations increased dramatically, air-to-air combat losses fell to 511 aircraft. Multiple factors contributed to this decline: better aircraft, better tactics, better training, but ammunition effectiveness was consistently cited in after-action reports as a primary factor. The economic impact was also significant. It cost approximately 75 cents to manufacture a single M8 API round in 1943, equivalent to about $13 today. Compare this to the cost of losing a fighter. A P-51 Mustang cost $50,985 to manufacture, plus roughly $100,000 to train its pilot. If the improved ammunition reduced the number of aircraft lost by just 1%, it paid for itself many times over. By conservative estimates, the M8 API program saved the United States military over $100 million in replaced aircraft and countless lives. Japanese military leaders recognized the threat posed by the new ammunition. Captured documents from 1943 to 1944 show that Imperial Japanese Navy aviation authorities issued multiple tactical directives attempting to counter American ammunition advantages. These included orders to avoid extended engagements with American fighters, to attack from positions where American fighters couldn't bring their guns to bear, and to focus on destroying American aircraft on the ground rather than in air-to-air combat. None of these measures proved effective. Some Japanese engineering teams attempted to retrofit existing Zeros with additional fuel tank protection, but these efforts were too little, too late. The 052C model, introduced in late 1944, featured rubber self-sealing compounds on some fuel tanks, but production delays and material shortages meant most Zeros never received these improvements. Even when they did, the self-sealing systems were inferior to American designs and offered limited protection against the M8 API's high-temperature burning. The M8 API's success led to a domino effect of tactical innovations. American fighter squadrons developed new attack patterns specifically designed to exploit the ammunition's capabilities. The Finger 4 formation, borrowed from German Luftwaffe tactics, allowed American fighters to cover more sky and engage targets from multiple angles. When combined with M8 API's extended effective range, these formations were nearly impossible for Japanese fighters to counter. Perhaps most importantly, the ammunition gave American pilots confidence. Multiple interviews with World War II fighter pilots reveal that confidence was a critical factor in air combat. Pilots who believed in their weapons fought more aggressively and effectively. The M8 API became legendary among American aviators. They trusted those silver-tipped rounds to do their job. This psychological advantage translated into better combat performance. By 1945, Japan's air forces had been reduced to a shadow of their former strength. While multiple factors contributed to this collapse, fuel shortages, pilot attrition, industrial degradation, the sustained effectiveness of American air-to-air combat capabilities played a crucial role. And at the heart of that effectiveness was a bullet with a silver tip that burned at 4,000 degrees. The story of the M8 API ammunition resonates far beyond World War II. It represents a case study in how technological innovation, tactical adaptation, and battlefield feedback can combine to create decisive military advantages. The lessons learned remain relevant to military planners and historians today. The first lesson is about the importance of ammunition design in determining combat outcomes. Too often, weapon systems are evaluated based on the platform, the aircraft, the rifle, the ship, while the actual munitions receive less attention. The M8 API demonstrates that even the finest weapons platform is only as effective as the ammunition it fires. American engineers understood this principle and invested heavily in ammunition research and development throughout the war. This investment paid enormous dividends. Modern military forces have internalized this lesson. The development of advanced ammunition types, from depleted uranium penetrators for tank guns to programmable airburst rounds for automatic cannons, reflects continued recognition that munitions technology is a critical combat multiplier. The U.S. military spends billions annually on ammunition research, development, and procurement, maintaining technological advantages that trace their lineage directly back to innovations like the M8 API. The second lesson concerns the interplay between design, production, and logistics. The M8 API wasn't just a brilliant design. It was a design that could be manufactured in enormous quantities with acceptable quality control and distributed across a global theater of operations. American industrial capacity made this possible, but it required careful coordination between designers who understood what was needed, manufacturers who could produce it reliably, and logistics officers who could get it to the right place at the right time. This lesson has become even more relevant in modern warfare. The U.S. military's concept of operational logistics, ensuring that forces have the right equipment, in the right quantities, at the right place and time, owes much to lessons learned during World War II. The ability to project not just military power but logistical support power remains an American strategic advantage today. The third lesson is about tactical adaptation. The M8 API ammunition didn't come with an instruction manual for optimal use. Squadron armorers and combat pilots figured out through experimentation that loading predominantly API belts maximized effectiveness. This represents bottom-up innovation, solutions emerging from the people closest to the problem rather than being dictated from headquarters. The military's willingness to allow this kind of experimentation and then rapidly disseminate successful innovations across the entire force was crucial to victory. Modern military organizations continue to struggle with the balance between standardization and adaptation. The most effective forces are those that can maintain doctrinal consistency while remaining flexible enough to incorporate innovations from the field. The U.S. military system of after-action reviews, lessons learned databases, and rapid fielding of new technologies reflects continued commitment to this principle. The fourth lesson concerns the value of understanding your enemy. American intelligence officers' discovery that Japanese aircraft lacked armor and self-sealing fuel tanks was crucial to developing ammunition that could exploit those vulnerabilities. This represented excellent intelligence work, not just gathering information, but analyzing it and recognizing its tactical implications. Combined with the technical capability to develop appropriate ammunition, this intelligence advantage proved decisive. In contemporary military planning, this lesson translates to the importance of comprehensive intelligence gathering and analysis. Understanding enemy capabilities and vulnerabilities remains as crucial today as it was in 1943. Whether dealing with improvised explosive devices in Iraq or anti-access/area denial systems in the Pacific, American forces succeed when they combine accurate intelligence with appropriate technological responses. The fifth lesson is about the human dimension of military technology. The M8 API didn't win battles by itself. It won battles because skilled pilots employed it effectively. Training programs had to adapt to teach pilots how to maximize the ammunition's potential. Confidence in the weapon system encouraged more aggressive tactics. This human-technology interface was critical to success. Modern military technology has become far more sophisticated, but the human dimension remains central. Whether training fighter pilots to employ precision-guided munitions or teaching soldiers to operate unmanned aerial systems, the military must ensure that human operators can effectively utilize technological capabilities. The investment in training must keep pace with investment in technology. The sixth lesson concerns the importance of continuous improvement. The M8 API wasn't the end of ammunition development. It was one step in an ongoing evolution. During the war, engineers continued refining the design, leading to variants like the M20 API-T, with improved tracer, and eventually the M23 incendiary round. This continuous improvement mindset ensured that American forces maintained their ammunition advantage throughout the conflict. Today, this translates to sustained investment in research and development even when existing systems work well. Potential adversaries are always developing countermeasures, and technological superiority requires constant innovation. The U.S. military's commitment to science and technology funding reflects understanding of this principle. The seventh and perhaps most profound lesson is about how wars are won. Popular imagination tends to focus on dramatic moments, dogfights between aces, carrier battles, amphibious assaults. But wars are ultimately won through accumulated advantages in thousands of small things. Better ammunition was one of those small things that, multiplied across millions of rounds fired in thousands of engagements, made an enormous difference. This lesson has implications beyond military affairs. In business, engineering, science, in any competitive endeavor, success often comes from superior execution of fundamentals rather than revolutionary breakthroughs. The M8 API wasn't a revolutionary concept. Incendiary ammunition had existed for decades. What made it revolutionary was executing the concept better than anyone else and deploying it more effectively. Looking back at the Pacific War, we can trace a direct line from the introduction of M8 API ammunition in early 1943 to the total collapse of Japanese air power by 1945. The ammunition didn't single-handedly win the war, but it was an essential component of victory. Combined with better aircraft, better tactics, better training, and overwhelming numerical superiority, it helped create an air combat environment where American pilots could operate with increasing confidence while Japanese pilots faced mounting losses they couldn't sustain. The human cost of the Pacific War was staggering. Over 100,000 Americans died in the theater, and Japanese casualties exceeded 2 million. We can't know with certainty how many lives the M8 API saved by helping to end the war more quickly, but the ammunition's contribution to American air superiority certainly shortened the conflict. Every month the war ended earlier saved thousands of lives on both sides. Today, M8 API ammunition is obsolete, replaced by far more sophisticated munitions. But examples are preserved in museums around the world. Their distinctive silver tips a reminder of the innovation and sacrifice of the greatest generation. The Browning M2.50 caliber machine gun, however, remains in service, a testament to John Browning's genius. Modern M2s fire advanced ammunition types that make the M8 API seem primitive, but they still use the same basic action, the same caliber, the same fundamental design. For collectors and historians, original M8 API rounds have become sought-after artifacts. They represent a tangible connection to a decisive moment in military history. Veterans who handled these rounds, the armorers who loaded them, the pilots who fired them, remember them with reverence. Those silver tips saved my life more times than I can count, one B-17 gunner recalled in a 1995 interview. I don't know where I'd be without them. Probably at the bottom of the Pacific. The story of the M8 API reminds us that military superiority isn't achieved through any single innovation, but through systematic excellence across all aspects of warfare, technology, training, logistics, tactics, leadership. It reminds us that seemingly small innovations can have enormous impacts when properly employed. And it reminds us that victory in war comes at tremendous cost, even when fought with the best weapons and the bravest warriors. As we face contemporary security challenges, these lessons remain relevant. Technological advantages must be pursued relentlessly. Logistics must be robust and flexible. Training must be rigorous and adaptive. Intelligence must be accurate and actionable. And most importantly, we must never forget the human cost of warfare and must work to prevent conflicts whenever possible, while remaining prepared to win them when necessary. Before you go, hit that subscribe button and ring the notification bell so you don't miss our next deep dive into military history. Drop a comment telling us what topic you'd like us to cover next. And remember, sometimes the difference between victory and defeat comes down to something as small as a bullet with a silver tip, fired by a pilot who trusted it with his life. That's the kind of detail that changes history. Thanks for watching. Until next time.